Welcome to Deep Space Drift. Tonight's journey follows a cosmic object that breaks expectations without being a black hole, a magnetar, a small remnant with a magnetic field so extreme that even empty space behaves differently nearby. Settle in as the story moves from quiet dust and soft gradients to the edge of what observation can truly confirm. If this calm science sleep documentary is helping, please like the video and subscribe to Deep Space Drift for more long-form space stories made for rest. Somewhere in the Milky Way, a dead star holds a magnetic field so intense that empty space no longer behaves as simple emptiness. A Magnetar is a neutron star whose magnetism becomes the main architecture around it. In that region, darkness is not uniform. A thin shell of old gas drifts outward in a wide oval. Its brightness fades along a smooth gradient like mist thinning over a cold valley at night. Near the centre sits a remnant so compact that size becomes misleading. Its body spans about 20 kilometres close to the width of a large lake. Yet its mass rivals that of the Sun, folded into a volume that leaves almost no room for ordinary matter. That single compression is the first rule it breaks. It shows that smallness can still dominate a region of space through density alone. The shell offers a slow scene for the mind to rest on. Faint filaments lace the expanding gas. They curve and fold where the flow meets thinner regions. Dust grains scatter the dim glow into a soft halo. The halo looks thicker on one side, like smoke settling into a shallow basin. That asymmetry is not decoration. It is a quiet clue that the remnant moves through a medium. It is also a clue that an explosion is still unfolding. The blast begins in less than a second, yet the visible shell takes centuries to stretch and thin. Inside the compact remnant, the usual emptiness inside atoms cannot survive. In ordinary solids, most volume is space. Nuclei are tiny islands. Electrons are wide clouds. Under the crush of a stellar core, that spacing fails. Protons and electrons combine into neutrons. Neutrons then pack close together with almost no gaps. Neutron matter is matter compressed until atoms lose their separate identities. A simple analogy helps. Dry sand holds air pockets. The same sand wetted and pressed becomes a heavy paste with far less space inside. In the stellar remnant, the pressing is gravity. The result is a body where a small distortion cannot dissipate gently. It tends to propagate because the material has nowhere to yield. That explains why tiny changes can matter on a star that looks so small from afar. Magnetism then steps forward as the second core feature. In many environments, magnetism is a subtle guide. Here it acts like tension built into the fabric around the star. Field lines arc outward and loop back. They form corridors that favour certain paths and resist others. Charged particles, if present, would slide along those corridors and struggle to cross them. The geometry can be pictured as layered sheets and loops. Some regions are dense with lines, some are sparse. Where the field changes rapidly, forces change rapidly too. That creates steep gradients that can store energy without visible motion. In some zones, the lines crowd together. In other zones, they open like a fan. Where crowding is strongest, a small shift can change the whole balance. A quiet unlock follows from that picture. Energy can be stored in shape alone even when matter hardly moves. A second slow visual anchor settles in close. Near the surface, a thin haze of plasma can form a faint veil. The veil is not steady. It stretches into long strands and then thins again, like fog pulled into streamers by a steady mountain wind. The strands follow the invisible arcs. They bend in broad curves. Their edges brighten where the density is slightly higher. The scene remains quiet, but it reveals structure. It shows that magnetism can create shapes without solid walls. It also hints at a boundary where ordinary intuition starts to slip. The third feature arrives through the crust. The surface is not a gentle sea. It is a rigid skin over denser layers. The crust is thin compared with the whole star, yet it carries immense stress. Pressure rises rapidly with depth. Gravity steepens over a short distance. The field adds another grip, like a tightening band that resists change. Over time, the magnetic geometry evolves. It tries to relax into a simpler shape. The crust resists that rearrangement. Stress builds slowly. Then a threshold is crossed. A starquake is a sudden slip in the crust. It is not loud in any air. It is not a sound. It is a motion and a release. The release can be brief, but its effect can spread along field lines through a large volume of space. The field does not vanish. It rethreads. Loops tighten and then loosen. When the geometry changes quickly, the surrounding plasma can be driven outward. Light then emerges in harder forms that travel far before fading. On the scale of a single second, the change is sudden. On the scale of the shell, the event is only a flicker on a centuries-long drift. A third visual anchor comes without drama. The surface can be pictured as dark rock under a hard distant light. Hairline fractures trace branching paths. Some cracks end abruptly. Some join into longer seams. Along a seam a ridge rises. Adjacent slabs settle into a new alignment. Above the seam, the surrounding plasma veil brightens for a short time. Light behaves as sharp pulses when the release is sudden. The pulses then fade. The surface returns to near stillness. The shell, far outside, continues to drift as if nothing happened at all. A limit appears that must be held gently. The interior cannot be seen directly. No view can look through that density. The field cannot be photographed as a line in space. Only indirect traces exist. A signal would arrive as timing patterns, as shifting colours, as brief flashes that suggest reconfiguration. Those hints depend on models. Models have resolution limits. They simplify geometry and material behaviour. Two different internal layouts can produce similar outward patterns. The precise map of the hidden layers remains uncertain, even when the outer behaviour looks clear. The scene then eases back out to the shell once more. Filaments continue to curl as the remnant's past expands into the surrounding medium. Over thousands of years, the magnetar cools and its field slowly relaxes. The crust settles into new stress patterns. Bursts become rarer. The halo thins. At a distance, the system looks calm again. The next step is to approach the compactness itself, and to see how rotation and density set the stage for the field. The calm exterior hides the extreme rules operating beneath. The following section turns that calm into a clearer map of size spin, and how time is marked near such density. A magnetar can seem still from far away, yet its spin quietly organizes everything nearby. The remnant rotates, and that rotation becomes the simplest clock that space can offer. At this distance, the body looks like a dark bead inside a thin haze. The haze is not uniform. It gathers into faint arcs that brighten and fade as the field guides charged matter. Near the magnetic poles, the surface is not smooth in behaviour. Heat and particles concentrate into small regions. Those regions create narrow cones of radiation that point outward. As the star turns, the cones sweep through surrounding space. The sweep is steady even when the environment is chaotic. The first calm unlock is that a pulse does not require an explosion. It can come from a turning geometry. The rotation itself is a mechanism for rhythm. In many magnetars, the rotation period is about 5 seconds, like a slow blink in darkness. That number is gentle, but it carries a deeper meaning. A body this compact can spin with remarkable regularity. The spin rate changes slowly over years. It does not wobble wildly from moment to moment. The reason is not calmness. It is inertia concentrated into a small volume. With so much mass packed close, the star resists sudden changes in its spin. The surrounding field and plasma can tug on it, but the response is measured. A slow, visual anchor settles in close. A thin veil of particles hovers above the surface. It forms a faint ring like mist lying along an invisible contour. The ring is not a hard band. It is a zone where the plasma density is higher. It glows slightly more than the surrounding space. As the star rotates, the ring does not spin as a rigid hoop. It shifts and shimmers, It breaks into strands that align with field lines. Those strands drift outward and then fold back. Their edges brighten where the field tightens. The image stays quiet and simple. It shows that rotation is not a decoration added later. It is part of the structure that organizes motion and light. Another unlock follows from the same picture. Rotation and magnetism interact through torque, a turning force. The field pushes on escaping particles and radiation. That outflow carries away angular momentum. Angular momentum is stored spin. Over time it drains. The star slows. The slowing is steady rather than dramatic. A change of a fraction of a second across years can be enough to measure in principle. The deeper point is more important than the detail. A magnetar does not need to be fast to be extreme. Its magnetism can dominate even when the spin is slow. The spin simply makes the dominance visible as rhythm. A natural analogy helps the mind stay calm. A falling seed can whirl as it descends. Its wings catch the air and enforce a stable spin. The seed slows its descent by turning. It does not need speed to be steady. It needs shape and balance. The magnetar is not a seed and space is not air. Yet the analogy carries a single safe idea. Rotation can be stabilized by structure. In the magnetar, the structure is density in the field. The stability matters because it turns a hidden object into a readable pattern. A second visual anchor arrives farther out. A broad patch of dust floats near the remnant. The dust is almost invisible most of the time, then a faint sweep of illumination passes across it. The sweep is narrow and clean. It moves with the magnetar's period. The dust brightens along a thin stripe. The stripe travels across the patch, then disappears. The patch returns to darkness. The motion repeats. The scene resembles moonlight sliding across rippled water, even though there is no water. It is simply scattering. It is simply geometry. The quiet payoff is that the environment can act as a screen. It can reveal a beam without any solid surface. It can show rotation at a distance, measured in light travel time rather than meters. Scale then shifts gently. Near the surface, the turning is immediate. The crust and the field move through their cycle each few seconds. Farther out, the pulse becomes a delayed pattern. Light takes time to cross the surrounding region. A change at the star arrives at a distant dust sheet later. The system contains many clocks at once. The rotation is one. The light travel time is another. The cooling of the surface is slower still. Over thousands of years the temperature falls. The outflow weakens. The ring-like haze thins. The rotation continues, gradually slowing under the steady loss of angular momentum. A magnetar can cross from active to quiet without any single moment that marks the change. The world simply relaxes. A soft limit of observation appears within this calm. The beam is not a solid cone that can be photographed from the side. Only its intersection with surrounding material can be noticed. The true shape of the beam remains uncertain. A narrow beam and a wider beam can produce similar pulses if the viewing geometry differs. The angle between the spin axis and the magnetic axis cannot be measured directly. It must be inferred from pulse shape and from polarization patterns. Those inferences rely on models with finite resolution. The plasma distribution is not known in full detail. Small changes in that distribution can mimic changes in geometry. Timing itself also has limits. Magnetars show timing noise. Their spin rate can wander slightly because the magnetosphere rearranges. A clean clock becomes a clock with gentle jitter. The jitter does not erase the rhythm. It simply blurs the path back to a single perfect model. The third calm unlock is that uncertainty does not remove meaning. It narrows what can be claimed. It keeps the story grounded in what signals can truly support. The view then returns to the surface in imagination. The polar regions glow faintly. The glow is uneven with boundaries that look sharper in some directions. A thin shadowed belt encircles the star where emission is weaker. Above it, a curtain of particles rises and falls along field lines. The curtain is not a wall. It is a gradient in density. Where it is thicker, light scatters more and appears softer. Where it is thinner, the beam edge looks cleaner. The rotation turns these patterns through space. The periodic sweep remains gentle. It is not a siren, it is a slow turning of geometry. The section eases toward the next checkpoint. Rotation explains how a compact remnant can announce itself through rhythm. The next step is to see how the magnetic field reaches such strength, and how compression turns a familiar field into something that reshapes space. The strangest part of a magnetar is not its mass or its spin, but how its magnetic field becomes a kind of structure in space. That field grows strong because collapse squeezes the same lines into a much smaller region. In that region, the surface appears as a dark sphere with a faint luminous band hovering above it. The band is not a ring of rock. It is a thin layer of plasma held in place by magnetic geometry. Its brightness changes along a smooth gradient. One edge looks sharper. The other fades into a soft haze where particles thin out. The first unlock is simple. A magnetic field can be strengthened without adding anything new. It can be intensified by compression alone. A familiar field in a large star becomes unfamiliar when folded inward. The process resembles a rubber band stretched wide and then gathered into a tight coil. The material does not change, the spacing does. Tension increases because the same length is forced into less room. That is the quiet heart of the magnetar. A collapse takes a field that once spreads through a vast interior. It then confines that field into a compact remnant where distances are short. In such conditions, changes in geometry become dramatic. A small twist near the surface can reorganize a long loop far above it. The crust holds the twist. The magnetosphere responds. The result is stored energy in the shape of invisible lines. Field lines become more than directions. They become pathways and boundaries. Where they converge, motion is squeezed. Where they diverge, motion can spread. The second unlock follows at once. The magnetosphere behaves like a flexible cage. It is not solid, but it can still confine and guide. A slow visual anchor settles close to the star. Above a polar region, a pale sheet of plasma hangs like a translucent veil. It drapes along curved lines that arc outward and return. The veil is faint and layered. Some layers look denser and slightly brighter. Between layers, darker gaps appear. The pattern suggests a stack of thin curtains. Each curtain is drawn into a different curve. Where the curves crowd together, the glow intensifies. Where they spread apart, it thins. The edges shimmer with subtle scattering as particles drift. The scene stays calm and steady. It gives a place to rest while the mechanism unfolds. Magnetic pressure becomes the next concept kept gentle. Magnetic pressure is force from a field that resists being compressed. It acts like a spring in space. When field lines are packed, the pressure rises. It pushes outward against confinement. The crust and gravity provide confinement. The magnetosphere becomes the region where this balance plays out. One number anchors the scale safely. A typical magnetar field is about 1,000 trillion times stronger than Earth's field. That is like placing a small household magnet beside a planet-sized one, then removing the planet and keeping the strength. The comparison is not precise in detail. It is a way to keep the scale inside a quiet imagination. With that strength, the field can influence how particles move even far from the surface. Charged particles spiral tightly around lines. Their sideways motion is restricted. Their preferred motion becomes along the curve. That restriction creates thin channels. It also creates sharp boundaries where regions of different density meet. Those boundaries can store energy. They can also become sites where the field abruptly changes shape. A micro payoff arrives from this picture. Bursts can be triggered by geometry, not by fuel. If the field rearranges quickly, it can drive particles outward and generate intense radiation. The energy originates in the field itself. It is the release of stored tension. The trigger may be a crust slip. It may be a slow drift that reaches a tipping point. Either way, the key is the same. A magnetar can flare because a configuration becomes unstable, then relaxes. The flare is a mechanical event in a field. It is not a chemical event. It is not a burning. The next visual anchor comes at a slightly larger distance. A loop of glowing plasma extends outward like a luminous arch. Its base is close to the star. Its top rises into darker space. Along the arch, brightness is not uniform. It forms beads and knots where density is higher. Between knots, faint gaps appear. The arch quivers slightly. The quiver is not visible as a shake of the star. It is a slow shifting of where particles collect. The arch then thins. It stretches. It becomes a fainter curve and finally dissolves into the surrounding darkness. The scene shows a boundary that exists only because the field makes it. It is a structure made of direction and constraint. Scale shifts gently from the near surface to the outer magnetosphere. Near the star, a meter matters. A small displacement changes local stress. Farther out, the same displacement is negligible. Yet the field connects these scales. A twist at the surface can propagate outward along a line that extends thousands of kilometers. The effect travels as a wave in the field and plasma. The wave can reorganize the arch and the veil. Timescales shift as well. The rearrangement can occur in less than a second. The cooling and settling of the crust can take years. The overall decay of the field can take thousands of years. A brief change sits inside a long, quiet life. This layered timing keeps the environment in a gentle rhythm. It also explains why a magnetar can appear calm for long stretches. Then it can flare without warning. A limit of intuition arrives here and it stays soft. The magnetosphere cannot be seen directly as a map of lines. Only emissions are visible. Those emissions depend on particle density and energy. The density is not constant. It changes after each burst. It changes with slow leakage. Models must assume distributions. They must assume how plasma fills loops and sheets. Those assumptions are uncertain. Two different field geometries can produce similar light curves if the plasma is arranged differently. The true three-dimensional shape remains partly hidden. Observation is limited by distance and by the indirect nature of the signal. A signal would carry information only along certain channels. It would miss the quiet regions that emit little. That is the boundary of knowledge. The field is understood through traces, not through direct measurement at every point. The section returns to the calm band above the surface. Its edge sharpens as the field tightens. Then it softens again as particles thin. The surface below remains dark and compact. The shell far outside continues to expand indifferent to the small reshaping near the core. The next step is to connect this field geometry to the solid crust and its stored strain. The following section moves toward the crust as a reservoir of stress and toward the gentle mechanics of a starquake. A magnetar holds its most dramatic changes beneath a surface that looks almost unmarked from afar. The crust stores stress because the magnetic field keeps trying to shift into a simpler shape. At this distance, the star is a dark point with a faint uneven glow near two regions. The glow is not smooth. It has a sharp boundary on one side and a softer fall-off on the other. That boundary is a physical detail of the environment. It is the edge of a hotter patch and a denser veil above it. The first unlock is calm and direct. A sudden burst can begin as a small slip in a solid skin. The slip does not need a large movement. It needs the right place and the right tension. The crust is thin compared with the star, yet it is rigid. It is also under pressure that rises quickly with depth. Under that pressure, the crust behaves like a single locked plate. It can bend a little. It can hold strain for a long time. It cannot flow like a liquid. The magnetic field pushes on it through the base of the magnetosphere. The push is not constant in direction. It drifts as field lines slowly rearrange. That drift is gentle. It is measured in years and decades. The crust follows until it cannot. Then it resists. Stress accumulates at boundaries between regions that prefer different shapes. Those boundaries can be imagined as seams. They can concentrate strain the way a crease concentrates pressure in folded fabric. The core mechanism stays simple. A stored imbalance grows, a threshold is crossed, a fracture or a slip occurs. Starquake is a sudden adjustment of the crust. It is not sound in air, it is motion in a solid under extreme conditions. The analogy is quiet and ordinary. A dried mudflat holds a pattern of cracks after water leaves. The surface shrinks. It cannot shrink smoothly. It breaks along lines of weakness. The cracks relieve tension. The Magnetar crust does not dry. It does not shrink from evaporation. Yet the idea remains safe. A rigid surface can release stress by breaking along a line. The release can be quick even if the build-up is slow. The second unlock follows immediately. The crack is not the main energy source. It is the switch that allows stored magnetic stress to reconfigure. A slow visual anchor forms on the surface. A broad dark plane stretches across the star lit by a faint uneven glow. Across that plane a pale fissure appears. It is a thin line that branches in two. One branch curves, the other runs straighter and then stops. Along the fissure the crust on one side sits slightly higher, like a ridge made by a subtle shift. The ridge casts a narrow shadow into the dim light. The shadow is sharp at first. It softens where a thin haze above the surface scatters the glow. The line does not widen into a canyon. It remains a hairline feature in a world where thickness is measured in layers of compressed matter. A small slip does not need a wide opening. It needs only to move stress from one locked arrangement to another. Above that fissure, the magnetosphere responds. Field lines anchored in the crust are forced into a new alignment. A twisted bundle can unwind a little. When it unwinds quickly, energy moves outward. Particles are accelerated along the curved paths. Radiation is released in a short interval. The release can be intense even if the fracture is small. The reason is the stored field energy in the surrounding space. A small change in anchoring can alter a large loop. It is like loosening a knot that holds tension in a stretched cord. The knot is small. The tension it controls can be large. A second visual anchor arrives a short distance above the surface. A loop of faint light forms like a curved ribbon. Its inner edge is brighter, its outer edge fades. The ribbon thickens near the base where particle density is higher. It thins toward the top where lines spread apart. For a moment the ribbon looks stable. Then it develops a ripple. The ripple travels along the curve. It gathers into a brighter knot. The knot slides, then disperses into a softer glow. The loop remains, but its structure changes. The scene shows how motion can occur without any solid object moving through space. It is a rethreading of constraints and flows. The scale shift comes gently. Near the fissure, the slip can occur in a fraction of a second. The magnetosphere reorganizes on that short time. Farther out, the effect can spread through a region thousands of kilometers wide. The light leaving that region takes time to cross it. The burst can be short at the surface. The afterglow can last longer as particles settle and cool. Over years, the crust continues to creep. It builds stress again. Over thousands of years, the magnetic field slowly relaxes, and the overall activity declines. The same object contains events that last less than a second, and trends that last longer than recorded history. That layered timing is part of the calm. It explains why long quiet periods are normal. It also explains why a brief flare can be part of a slow decay. A limit of intuition and observation appears, and it is specific. The fissure cannot be seen directly at any great distance. The surface is too small and too far. The crustal motion is inferred from changes in radiation and timing. Those changes can have multiple causes. A magnetosphere rearrangement can mimic a crust slip. A crust slip can occur without a strong radiative burst if the magnetosphere remains stable. Models attempt to connect light curves to stress patterns. Those models require assumptions about crust strength and field geometry. Both are uncertain. The crust may have impurities and layered phases. Those layers alter where fractures prefer to form. The field may have hidden components beneath the surface that cannot be reconstructed from external signals. Observations also have limited time resolution. A very fast event can be smeared into a single spike. The exact sequence of crust motion and magnetosphere response may be lost inside that blur. What remains is the broader picture. Stress builds, a threshold is crossed, a reconfiguration releases energy. The scene returns to the dim glow boundaries near the poles. The boundary shifts slightly after a burst. It becomes more ragged. Then it smooths again as the plasma veil thins and settles. The shell far outside continues its slow expansion. Its filaments do not react to a single quake. The magnetar does not change its overall size. It changes its configuration. The next section moves outward into how the magnetosphere traps and guides particles after a quake. The focus shifts from cracks in a crust to corridors in space, and to how confinement creates rhythm and release. After a starquake, the space around a magnetar becomes a place where motion is guided more than it is free. The magnetosphere confines charged particles, and that confinement turns a brief disturbance into a longer glow. In that region, the scene is delicate. A faint arc of plasma hangs above the surface like a curved ribbon. The ribbon has a bright inner rim and a softer outer edge. Along the rim, small knots appear where density gathers. Between knots, the glow thins into darker gaps. The first unlock is quiet. A burst can fade quickly at the surface, yet linger in the magnetosphere as trapped motion. The trap is not a cage of walls. It is a set of preferred paths created by field lines. Particles spiral around those lines. Their sideways drift is limited. Their forward motion follows the curve. That makes long, narrow corridors in space. It also makes boundaries because different corridors can hold different densities. Those boundaries can look like sheets. They can look like layered veils that overlap. Magnetosphere is the region where magnetic fields control the surrounding plasma. The definition is short. The picture is simple. It is a volume shaped by invisible lines filled with matter that cannot move freely. That matters because it explains why a magnetar can stay luminous after a sudden event. The glow is not only from the surface, it is from the extended environment that stores energy in motion and field geometry. A single number anchors the scale gently. The magnetosphere can extend tens of thousands of kilometers from the star like a web stretched wider than an entire small planet. The comparison keeps the mind calm. It shows that a city-sized object can influence a region that is vastly larger than itself. The scale shift is built into that contrast. Near the surface, the crust slips and settles over meters. Far above, the response occupies distances that dwarf mountains and oceans on Earth. Yet the connection remains tight. A small twist near the surface can propagate along a line that spans that whole reach. A slow visual anchor forms around the arc. The ribbon brightens at one end. A ripple travels along it. The ripple gathers into a knot, then spreads into a softer glow. The knot is not a solid clump. It is a region where particles crowd. The crowding increases scattering. It also changes how the light emerges, making the edge sharper for a moment. Then the knot disperses. The ribbon returns to a smoother gradient. The scene stays gentle and repetitive, like a tide of brightness that never becomes loud. Another unlock follows from this motion. Trapping creates delays. If particles are guided along long paths, their energy is released gradually. Some particles radiate as they spiral. Some collide with thinner regions and slow. Some are reflected where the field strengthens and the corridor narrows. The magnetosphere becomes a reservoir of short-lived populations. It can fill after a burst and then drain. That fill and drain can create afterglows. It can also create repeated pulses if the star's rotation sweeps bright regions through space. The mechanism is not a single flash. It is a system that rings and settles. An everyday analogy keeps the idea steady. A long hallway can carry footsteps farther than an open field. Sound in a hallway reflects and lingers. In an open field, it disperses quickly. Space has no air here. Yet the analogy holds one safe point. Confinement makes an effect last longer. In the magnetosphere, confinement is magnetic rather than physical. The corridors reflect and guide motion. The glow becomes a lingering trace of a brief trigger. A second visual anchor appears farther out. A broad sheet of faint light forms like a translucent curtain. The curtain has ripples across it. The ripples are bands of slightly different brightness. At the edges, the curtain frays into fine threads that curve back toward the star. The threads look like strands of silk caught in a slow current. The curtain is thicker near one side. It thins toward the other, fading into darkness. The thickness is a gradient in particle density. The gradient makes the boundary visible without any solid surface. The gentle payoff is that structure can be revealed by the way it fades. Edges and gradients are clues to confinement. They show where motion is allowed and where it is resisted. The story then steps through a checkpoint of time. Immediately after a quake, the magnetosphere can be crowded. The glow can be stronger. Over minutes and hours, it can soften as particles lose energy. Over days, it can thin further. Over longer periods, the system returns to a quieter baseline. This is a calm cascade. It turns a sudden event into a longer settling. The rotation of the star continues through all of it, providing a steady rhythm that can modulate brightness. In a single second, the quake triggers. In many hours, the environment relaxes. Over thousands of years, the overall field strength declines, and the capacity for large disturbances decreases. A magnetar holds short and long clocks at once. That layered timing is part of its strangeness. It is also part of its calm. A limit of observation appears in a precise way. The magnetosphere cannot be mapped as a full three-dimensional web. Its light is selective. It comes from where particles are dense and energetic. Quiet corridors may exist but remain unseen. The same observed pulse shape can be produced by different combinations of corridor geometry and particle distribution. Inference requires models. Models require assumptions about how plasma fills loops and sheets after a burst. Those assumptions are uncertain. Time resolution also limits certainty. A fast rearrangement can occur inside a brief spike that hides its internal steps. Distance blurs fine structure. The result is a careful picture rather than a complete one. Confinement is evident. Exact geometry remains partially hidden. The section returns to the ribbon close to the star. Its inner rim glows. Its outer edge fades. The knots drift and dissolve. The curtain farther out thins until only a faint haze remains. The shell of old gas beyond continues to expand without haste. The next checkpoint moves from trapped particles to light itself. The following section explores how extreme fields can alter the vacuum's behavior, and how that creates subtle changes in the way radiation travels outward. In the strongest magnetar fields, light can carry a subtle memory of the space it travels through. The vacuum itself behaves like a material, and that changes how radiation spreads outward. At this distance, the magnetar sits behind a thin haze that looks almost like frost in darkness. The haze is not uniform. It forms a broad fan shape on one side and a tighter plume on the other. The edges of both are smooth but distinct. Near the fan's rim, the glow is softer. Near the plume, the glow sharpens and becomes more needle-like. The first unlock is gentle. Empty space is not always an inert stage. Under extreme fields, it can influence light as if it had texture. Vacuum birefringence is empty space acting like a crystal for light. The definition is short. The picture is calm. In some directions, light passes with one character. In other directions, it passes with another. The effect does not split beams into two visible lanes in ordinary conditions. It alters the polarization and the spread in subtle ways. An everyday analogy helps without overstating. A clear pane of ice can look uniform. Under the right angle, faint internal layers appear. The layers slightly change how a dim lamp looks through them. The magnetar environment is not ice, yet the analogy holds a safe point. A medium can be invisible and still shape a beam. The second unlock follows. If space behaves like a medium, then direction matters. Light that travels across field lines can be affected differently than light that travels along them. That creates a kind of ordering in the radiation. It can make the glow appear smoother in one region and more sharply bounded in another. It can also make the pulse shape cleaner or more blurred depending on geometry. The change can be tiny in absolute terms, yet it can carry information. It reveals something about field strength and arrangement without showing the field directly. A slow visual anchor forms around this idea. A faint beam leaves the polar region and crosses a thin dust sheet. The dust is sparse. It catches only a small fraction of the radiation. Still, a delicate stripe appears where scattering is strongest. The stripe has a crisp inner edge. Its outer edge fades in a gentle gradient. The stripe drifts across the dust sheet as rotation carries the beam. Where the beam passes through denser magnetospheric haze, the stripe widens slightly. Where the path is clearer, it narrows. The scene stays quiet and precise. It shows a boundary created by light, not by walls. It also shows how the environment can soften or sharpen that boundary. A single number anchors scale and keeps it safe. The field strength needed for strong vacuum effects is around 100 trillion Gauss, like a storm of magnetism far beyond any familiar field. The comparison is not meant to be exact. It is meant to keep distance between ordinary experience and the Magnetar regime. In that regime, the vacuum is not a passive emptiness. It is a responsive background. This is the calm rule breaking. Light behaves as if it senses the field through which it moves. The idea can be held without heavy math. It is enough to know that the vacuum has quantum properties. Under extreme conditions, those properties become noticeable. Another micro payoff arrives. This effect offers a way to test the Magnetar environment without touching it. If radiation carries polarization patterns that match birefringence, then the environment is confirmed as extreme in a very specific way. It is not just bright. It is not just dense. It is in a regime where quantum behavior changes macroscopic signals. The consequence is gentle. Magnetars become natural laboratories for physics that is otherwise hidden. Yet this laboratory is not a place of instruments. It is a place where the universe's own rules provide the imprint. A second visual anchor arrives farther out where the beam diffuses. The glow becomes a soft oval around the star. Within the oval, faint bands appear like concentric smudges. The bands are not rings of matter. They are zones where polarization and scattering make the brightness slightly different. The inner band is sharper. The next band is more diffuse. Their edges overlap, forming a layered look like smoke in still air. The layering shifts slowly as the magnetosphere relaxes after earlier activity. The bands never become bright enough to be harsh. They remain a gentle texture on a dim field. Scale shifts again. Near the surface, the field is strongest and the vacuum effect is most pronounced. A path of a few kilometers can matter. Farther out, the field weakens. The vacuum becomes closer to ordinary emptiness. The effect fades. Over time, scales the field itself decays. Over thousands of years, the region where the vacuum behaves like a crystal shrinks closer to the star. The same phenomenon exists in a brief pulse and in a long evolution. A flare can temporarily fill the magnetosphere with particles and alter the scattering environment. Then it drains. The birefringence effect remains tied to the field, but the visible imprint depends on what is present to scatter and radiate. The story then touches a clear limit of observation. Polarization is difficult to measure at distance. Signals are faint. They can be contaminated by scattering in intervening dust and gas. They can also be altered by the magnetosphere itself in ways that mimic birefringence. Distinguishing vacuum effects from plasma effects requires models of particle density and temperature. Those models have uncertainties. Geometry adds more uncertainty. A small change in viewing angle can change the inferred polarization pattern. Time variability adds another layer. If the magnetosphere rearranges between measurements, patterns can drift. The limit is not ignorance, it is ambiguity. Multiple explanations can fit similar data when resolution and signal strength are limited. That boundary of certainty is part of the magnetar's calm mystery. The section returns to the beam crossing the dust sheet. The crisp edge softens for a moment as the path passes through thicker haze. Then it sharpens again as the beam clears. The oval glow around the star fades gradually at its edges. The layered bands dissolve into a smoother halo. The shell far outside continues to expand. Its filaments remain slow and indifferent. The next checkpoint moves back from light to matter. The following section explores how energy leaves the magnetar as bursts and afterglows, and how the environment decides whether a flare is brief or lingering. A magnetar flare is not only a flash from a surface, but a choreography between trapped particles and escaping light. The duration of a flare depends on how the magnetosphere fills and then drains. In that region, the near space is layered. A bright core of glow sits close to the star. Around it lies a softer halo. The halo has a sharp inner boundary and a fading outer edge. Across the halo, faint striations appear like brush strokes, each one slightly brighter than the next. These are density gradients in the plasma. They mark where particles are more numerous and where they thin out. The first unlock is gentle. A short trigger can produce a long afterglow because energy can be stored in motion, then released gradually. The trigger may be a cross slip or a rapid field rethreading. The afterglow is the settling. Particles spiral along field lines and radiate as they lose energy. Some travel outward and escape. Some remain confined in loops and sheets. Those loops behave like reservoirs. When they are full, the glow is stronger. When they drain, the glow softens and fades. The mechanism does not require a new burst each moment. It requires only the slow emptying of what was already injected. A single number anchors the scale of time. A typical afterglow can last about 1 day, like a warm stone that keeps releasing heat long after sunset. The comparison is not about temperature, it is about persistence. It keeps the mind steady as the scene stretches from seconds to hours. The flare itself can begin in less than a second. The magnetosphere can then stay unsettled for far longer. The scale shift is calm and clear. It shows how a compact event becomes a wide settling across a vast region. An everyday analogy supports the shape of the idea. A sponge soaked in water releases it slowly. A quick dunk fills it. A long drip empties it. The magnetosphere is not a sponge, yet the analogy carries a safe point. A reservoir can turn a brief input into a long output. The second unlock follows. The shape of the reservoir matters. Narrow loops hold particles close to the star. Wide loops allow larger volumes and longer travel paths. Particles in wide loops can take longer to radiate away their energy. They can also scatter light more, which softens edges and spreads the glow into a larger halo. Particles in narrow corridors can create sharper boundaries. Their emission can look like a clean band or a bright knot. The magnetosphere can contain both at once. That is why a flare can have a sharp initial spike and then a softer tail. The spike is the fast injection. The tail is the slow release. A slow visual anchor forms inside this settling. A broad arc of plasma glows above the star like a crescent. Its inner rim is bright and thin. Its outer edge is thicker and fades into darkness. Along the rim, a string of small bright beads appears. The beads drift. They merge into larger knots. Then they dissolve. Each change is slow enough to feel quiet. The crescent does not move like a thrown object. It reshapes as the distribution along the field lines evolves. The beads are density peaks. The fading is drainage. The crescent slowly thins until it becomes a barely visible veil. A micro-payoff comes from this scene. The flare's tail is not a separate phenomenon. It is the same energy redistributed in space and time. Another visual anchor arrives farther out where the halo interacts with a thin dust sheet. The dust is sparse and cold. It scatters a small fraction of the light. A faint ring-like glow appears on the dust sheet centered on the magnetar's position. The ring is not a physical ring in space. It is a light echo. Its boundary is sharp on the inner edge and softer on the outer edge. As time passes, the ring grows in radius across the dust sheet. The expansion is not motion of matter. It is the arrival of light at larger angles. The ring's brightness decreases as it expands. The scene stays calm and geometrical. It offers a way to see time as a shape. The payoff is immediate. A flare can illuminate distant material later, even after the magnetosphere has already begun to settle. The flare leaves footprints at different distances at different times. Scale shifts again from the near magnetosphere to far dust. Near the star, the field and particles define the glow. Farther away, scattering defines it. The same event is seen through different filters. The near region emphasizes confinement and release. The far region emphasizes geometry and delay. Over longer spans, the magnetar returns to a baseline glow. The reservoir's empty. The loops become less crowded. The halo thins into a faint haze. Over thousands of years, the field decays and the overall energy available for large injections declines. The system drifts toward quieter behavior. Yet even in that drift, small variations remain. A magnetosphere is never perfectly still. It is a dynamic balance between field geometry and plasma supply. A limit of observation appears and it remains specific. The flare energy cannot be fully measured at all wavelengths and all times. Some of it may be emitted in forms that are hard to detect. Some may be absorbed and reprocessed by surrounding material. Models must estimate how much energy stays in trapped particles and how much escapes promptly. Those estimates depend on unknown plasma density and composition. They also depend on the unknown three-dimensional structure of the field. A light echo can help constrain timing and geometry, yet even an echo depends on the distribution of dust. Dust is patchy. The ring may be incomplete. The boundary may be blurred by uneven scattering. Time resolution can miss the fastest part of a spike. Distance can blur fine structure in the halo. The exact partition between spike and tail remains partly uncertain. What remains robust is the process. Injection is fast. Reservoirs drain slowly. The scene returns to the crescent close to the star. Its beads fade. Its rim softens. The sharp inner boundary of the halo becomes less defined. The ring-like echo on the dust sheet expands until it becomes too faint to notice. The magnetar settles into a quieter glow. The next checkpoint moves from the timing of flares to the spectrum of light itself. The following section explores how gravity and the surface environment shift the energy of photons as they climb away from the star. Near a magnetar, light does not leave with the same energy it had at the surface. Gravity and the dense environment shift photons downward in energy as they climb away. In that region, the surface glow looks uneven. Two bright patches sit near opposite ends of the star's field geometry. Each patch has a crisp boundary on one side and a softer edge on the other. Between them lies a dim belt where emission weakens. Above the belt, a thin veil of plasma hovers and scatters the glow into a faint halo. The first unlock is calm. A photon can lose energy without losing speed simply by escaping gravity. That loss is gravitational redshift. The definition can stay gentle. It means light is stretched to lower energy as it climbs out of a deep gravitational well. The light still travels at the usual speed. Its wavelength becomes longer. The change is subtle but real. It matters because it carries information about how deep the well is. It also matters because it changes what the surface looks like from far away. A quiet analogy helps. A ball rolled up a hill slows as it climbs. It does not disappear. It trades kinetic energy for gravitational potential. Light cannot slow in the same way, yet the analogy holds one safe idea: climbing cost energy. For light, the cost appears as a change in wavelength and energy. The second unlock follows. This effect is strongest close to the surface where gravity is steep. It fades with distance. That creates a gradient in what can be inferred. Signals emitted near the surface carry the largest redshift imprint. Signals formed farther out carry less. In practice, this means that the same underlying radiation can be observed with different energy depending on where it originates. Surface emission is shifted. Magnetospheric emission is shifted less. Scattered emission is altered again by interactions with the plasma veil. The environment becomes a layered filter. A slow visual anchor forms at the edge of a hot patch. The patch glows with a pale intensity. Its boundary is sharply defined on one side like a shoreline in dim moonlight. On the other side, the glow fades over a smooth gradient into the darker belt. Above the boundary, a thin mist of particles brightens slightly where it is denser. The mist forms a shallow arc. The arc casts a faint shadow into the belt because scattering redirects light away. The shadow is soft. It is not a hard line. It is a gentle dimming that curves with the arc. The scene provides a physical detail that stays quiet and concrete. It also carries a payoff. The edge tells where emission changes and where scattering begins to dominate. A single number anchors the sense of gravity without heavy math. Near a neutron star, the escape speed is about half the speed of light, like trying to climb out of a pit so deep that even the fastest runners would struggle. The comparison is imperfect but calming. It signals depth without turning into a calculation. That depth explains why redshift matters here. The star's compactness makes gravity steep over a short distance. A photon leaving the surface climbs a significant fraction of the total gravitational drop within a few tens of kilometers. That is a small distance in space. It is a large distance in gravitational terms. The scale shift is gentle. It moves from kilometers near the surface to the vastness beyond, showing how quickly the effect fades as distance grows. Another visual anchor arrives farther out. A faint plume of light stretches along a magnetic corridor. Its core is brighter and narrower. Its edges are softer, where scattering spreads photons outward. Along the corridor, the colour of the glow shifts slightly. The change is not a sharp band. It is a gradual drift as photons travel and interact. The corridor appears like a slow brushstroke across darkness. Its leading edge is crisp. Its trailing edge fades. The image stays soft and restful. The micro payoff is immediate. Energy shifts can be read as a history of where the photons have been. A photon carries the imprint of gravity. It can also carry the imprint of scattering. Scattering is the second concept held in this section. Scattering is light changing direction by interacting with matter. The definition stays short. In the Magnetar environment, scattering happens in the thin plasma veil and in more distant dust. Each interaction can blur edges. It can also redistribute energy. A photon that is redshifted by gravity can then be scattered, mixing with photons from other regions. The observed spectrum becomes a blend. That blend carries information, but also hides details. The third unlock follows from that blend. A clean measurement of redshift is difficult because the environment is not transparent and simple. The photon's journey is layered. It begins deep. It climbs. It may scatter. It may join other photons. The final signal is a sum of histories. This is where the limit of observation appears, and it is specific. The surface cannot be resolved as an image at such distances. The redshift must be inferred from spectral features. Yet strong magnetic fields and hot plasma can broaden those features. Scattering can smear them. Different emission regions can overlap in energy. Models must separate surface emission from magnetospheric emission. They must assume temperature distributions across the surface. They must assume plasma densities along corridors. Those assumptions are uncertain. Even the geometry of the hot patches can change after bursts. A change in patch shape can mimic a change in inferred redshift. Resolution limits and signal noise add more ambiguity. The result is that redshift can be constrained but not pinned down with perfect certainty. That boundary is calm and honest. It does not remove the effect. It shows why the interpretation must remain careful. The scene returns to the hot patch boundary. The crisp shoreline edge softens as the plasma veil thickens slightly. Then it sharpens again as the veil drains. The dim belt remains as a quiet background. Farther out the corridor, plume fades into the surrounding haze. The gravitational imprint becomes less important as distance grows. The next checkpoint moves deeper into what lies beneath the crust, where matter may take on phases that cannot be directly observed. The following section turns toward the interior and the limits of inference from the outside glow. The inside of a magnetar is never seen yet, it quietly dictates what the outside can do. The interior composition sets how the crust flexes and how the magnetic field is anchored. At this distance, the star is a dim point with a thin halo. The halo is uneven. It forms a soft oval with a sharper rim on one side and a gentler fade on the other. That rim is a boundary where scattering becomes more efficient. Near the rim, the glow looks layered like faint bands stacked closely together. The first unlock is calm. The surface behavior can hint at the layers beneath even when those layers remain hidden. The magnetar is built in strata. The crust sits on denser matter. Below that, pressure rises beyond any ordinary solid. The material changes its rules. Neutron matter is matter where neutrons dominate and atoms dissolve. The definition is short and clean. The picture can remain simple. It is a substance so compressed that separate nuclei no longer keep their spacing. A familiar analogy keeps the mind steady. A layered dessert can look smooth from the top. Inside, the layers hold different textures. A cut reveals boundaries and transitions. The magnetar cannot be cut, yet the safe point remains. Layers can exist beneath a calm surface. Those layers control how stress travels and where it concentrates. The second unlock follows. If the interior is stiffer or softer in certain zones, then the crust above responds differently to the same magnetic push. Stress may pile up at specific depths. It may transmit efficiently in one direction and poorly in another. That changes where starquakes prefer to occur. It also changes how the magnetic field threads through the crust. The field is anchored in conductive material. If the conductivity varies by layer, the field evolves differently. The outer behavior becomes a map, but a blurry one. Bursts and timing noise offer clues. Cooling patterns offer clues, yet none of them show a direct picture. A slow visual anchor forms as a mental cross-section. The star is imagined as a dark sphere with thin, luminous skins. The outermost skin is a brittle crust. Beneath it is a smoother layer that appears darker and denser. Deeper still, a core region appears almost featureless, like a deep lake seen from above at night. Between layers, boundaries appear as curved interfaces. Each interface has a subtle change in shading. The shading is a gradient rather than a sharp line. That gradient suggests a transition rather than a hard wall. The scene stays calm and quiet. It gives a stable image while uncertainty is held gently. One number anchors scale and keeps it safe. The core density is about 100 trillion times the density of water, like compressing an ocean into the volume of a pebble. The comparison is not literal. It is a way to convey the distance from ordinary matter. It explains why intuition fails. At such densities, familiar materials are irrelevant. Even the idea of a crystal lattice becomes strained. The consequences reach outward. A dense interior means enormous pressure at the base of the crust. It means a crust that can crack yet remain under immense confinement. It means a magnetic field that can be held in place and twisted over time. A micro payoff arrives from this. The magnetar's violent moments are powered by deep stability. The crust can store stress because the interior and gravity keep it confined. Without that confinement, fractures would simply relieve stress gradually. Here, stress can build because the whole object resists reshaping. The extreme events are therefore linked to extreme compactness and deep layering. Another visual anchor appears in the outer glow. After a flare, the halo shows a faint band that drifts outward and fades. The band looks like a thin, dim ring segment rather than a full circle. Its inner edge is crisp, its outer edge is blurred. The band suggests a wave of particle density moving along certain magnetic corridors. That motion is guided by the field. Yet the field's anchoring depends on the deep layers. The exterior pattern becomes a shadow of interior conditions. The scale shift is gentle. A quake happens in a fraction of a second. The resulting afterglow can last hours. The deep interior evolves over thousands of years as it cools and as the field relaxes. The same object holds these timescales together. A second timescale shift appears in the cooling itself. Early in a magnetar's life, the interior is hotter and more dynamic. Later it cools and the crust becomes more rigid. Activity changes accordingly. The magnetar passes through phases. The glow-the-pulse behavior and the burst rate can all drift over long spans. The interior is the quiet driver of that drift. A limit of observation must be stated clearly. The interior composition cannot be determined directly from the outside. Different equations of state, meaning different rules for how matter behaves under pressure, can produce similar masses and radii. Those possibilities lead to different layer thicknesses and different core phases. Observations rely on indirect inference. Cooling curves depend on unknown magnetic geometry and surface composition. Burst behavior depends on both crust strength and magnetosphere configuration. Timing irregularities can be caused by magnetospheric changes rather than interior changes. Without a direct probe, multiple interior models can fit the same surface data. Resolution and signal quality limit which features can be distinguished. The boundary is not only technical, it is conceptual. Intuition cannot picture matter at that density. Models can, but models must be tested against incomplete data. This is the magnetar's quiet unknown. It is not a gap that invites fantasy. It is a controlled uncertainty that shapes cautious conclusions. The section returns to the layered cross-section image. The crust remains thin and brittle. The deeper layers remain smooth and dark. The interfaces remain gently curved. Above the surface, the halo continues to show soft bands and gradients. The shell, far outside, still expands, carrying the memory of the original collapse. The next checkpoint moves back outward to consequences. The following section explores how a magnetar's activity shapes the surrounding nebula over time, and how repeated outflows sculpt structure in a wider region. A magnetar seems small in isolation, yet its repeated outflows can slowly redraw the space around it. The surrounding nebula becomes a record of pressure timing and direction. At this distance, the expanding shell is no longer a uniform bubble, it is mottled. Its rim is brighter in some arcs and dimmer in others. Along the bright arcs, thin filaments braid together. Between them, darker lanes open like gaps in smoke. The edge has a clear boundary where the shell meets thinner interstellar gas. Inside that boundary, a softer glow fills the interior, fading toward the center. The first unlock is quiet. The nebula is shaped not only by the original explosion, but by what happens afterward. The magnetar adds energy in episodes. Each episode is small compared with the supernova as a whole. Yet over time, repeated additions can change the interior structure. The additions come as particle winds and bursts that push on the nebular gas. They inflate small cavities. They sharpen some filaments. They can also create asymmetry if outflow favors certain magnetic directions. The concept remains simple. Pressure drives expansion. Gradients form where pressure changes. Boundaries appear where flows meet. A calm analogy holds the idea without forcing it. A stream entering a pond creates layered currents. The pond already exists. The stream does not create the basin. It changes the patterns inside. The magnetar is the stream. The nebula is the pond. The safe point is that steady input can reorganize an existing volume. The second unlock follows. The nebula carries memory. Older structures are stretched. Newer structures sit on top as smaller ripples and cavities. This layering is visible as nested gradients. It is visible as arcs that look cleaner in some places and frayed in others. A slow visual anchor forms inside the shell. Near the center, a faint cavity appears like an oval clearing. Its boundary is slightly brighter than the region inside. Around the cavity, wispy strands curve and reconnect like threads pulled toward a gentle swirl. The cavity is not empty. It is lower density. Light from the cavity is weaker. The boundary is a pressure front. It marks where a magnetar-driven wind has pushed material outward. The oval is not perfectly centered. It is offset, suggesting motion through the surrounding medium or uneven density outside. The payoff is immediate. The magnetar's influence is not a point effect. It becomes a shaping force for a volume far larger than the star. One number anchors the scale safely. The shell can span about 10 light years, like the distance light travels in a decade. The comparison keeps the mind calm. It makes the scale tangible without a list of units. It also sets up a scale shift. The magnetar itself is only tens of kilometers across. The shell is trillions of times larger in extent. Between those sizes lies the magnetosphere, then the inner nebula, then the outer rim. A change that begins in a crack or a twist near the surface can ultimately contribute to structure across light-year distances. The connection is not direct in one step. It is a slow chain of pushes and relaxations. A second visual anchor arrives at the rim. A bright filament runs along the boundary like a thin, glowing rope. Its thickness varies. In places it narrows to a fine line. In other places it widens into a fuzzy band. Small knots sit along it at irregular spacing. The knots cast faint shadows into the interior glow because the densest regions absorb and scatter more. The shadows are soft and curved. They fade quickly as the interior glow fills them. The filament bends where the external medium is denser. It becomes sharper where the medium is thinner. The scene shows physical detail that is easy to hold. It shows how a boundary can look like a living outline without any intention or agency. Another micro-payoff follows from the rim. The brightest parts of the shell often mark where expansion meets resistance. Where resistance is higher, gas compresses. Compression increases emission. Where resistance is lower, expansion is freer, and the rim is dimmer. The nebula therefore becomes a map of its surroundings as well. It records not only the magnetar's activity, but the texture of the interstellar medium. The magnetar-driven winds add another layer of complexity. They can carve channels that vent energy toward weaker parts of the shell. They can also inflate interior bubbles that press on the rim from within. The result is a shell that is not a simple sphere. It is a patchwork of arcs and gaps. The narrative steps through time gently. The original supernova shock expands rapidly early on. Over hundreds of years it slows as it sweeps up material. Meanwhile, the magnetar's activity evolves. Early in its life it can be more energetic. Its winds can be stronger. Over thousands of years the field decays and the activity declines. The nebula's inner structures reflect these phases. Older cavities are larger and more diffuse. Newer cavities can be smaller and sharper. The shell's filaments stretch and thin as the entire structure grows. The scale shift is not only size, it is time. A burst lasts less than a second. A cavity grows over years. The shell evolves over centuries. The overall system relaxes over thousands of years. The same region holds these clocks together like layers of sediment in slow motion. A limit of observation appears and it remains specific. The three-dimensional shape of the nebula is hard to reconstruct from a two-dimensional projection. Brightness depends on density and temperature. It also depends on how much material lies along the line of sight. A filament can look bright because it is dense, or because it is a long column seen edge-on. Cavities can look empty because density is lower, or because emission is weaker at the observed energies. Models attempt to infer pressure and energy input from these patterns. Yet the distribution of surrounding gas is not fully known. Dust can obscure or scatter light. Some parts of the shell may be too faint to detect. Time sampling is limited. Changes over decades can be difficult to confirm. The nebula can therefore be read as a qualitative record more easily than a precise quantitative ledger. The record is real. The details are uncertain. The section returns to the offset cavity inside the shell. Its boundary remains faintly bright. The threads around it drift into softer haze as expansion continues. The rim filament holds its shape for a time, then slowly stretches and thins. The next checkpoint moves from the nebula to the long life of the magnetar itself. The following section explores how magnetism decays and how a once violent phase becomes quiet over many thousands of years. A magnetar does not stay extreme forever, but it does not become ordinary quickly either. The field decays and the activity softens, leaving a long, quiet afterlife of fading structure. At this distance, the nebular rim is faint and broken. Its filaments are thinner now. Some sections of the boundary remain bright arcs. Other sections are almost invisible. Inside the shell, the earlier oval cavity is larger and more diffuse. Its edge is less sharp. It is still traceable as a subtle brightness gradient. Near the centre, the magnetar's halo is smaller than before. It has a tighter core and a gentler outer fade. The first unlock is calm. Decay is a slow redistribution, not a sudden collapse of behaviour. The magnetic field loses energy through processes that turn ordered structure into heat and motion. Some decay happens in the crust where currents dissipate. Some happens through rearrangements that shed energy into the magnetosphere. The overall trend is a gradual weakening of the field's ability to store stress and to drive strong outflows. Field decay is the field slowly losing strength and complexity over time. The definition is short. The idea remains simple. A strong tangled configuration relaxes toward a simpler one. The second unlock follows. As the field weakens, bursts become less frequent and typically less energetic. The surface hot patches can cool and spread. The sharp boundaries of emission become softer. The magnetosphere becomes less crowded and less dynamic. A magnetar can still show pulses because rotation remains. Yet the imprint of extreme magnetism on the environment declines. The object moves through phases. An early phase where flares and afterglows are common. A middle phase where activity is intermittent. A late phase where the star is quiet and mostly cooling. A calm analogy helps. A charcoal ember glows bright at first. It then dims slowly while still holding warmth. The ember does not switch off. It drifts toward darkness. The magnetar is not burning charcoal, yet the safe point stands. A store of energy can drain over long periods, leaving a fading trace rather than a sudden end. A slow visual anchor settles on the star itself. The surface glow is now a broad, faint patch rather than a tight hot spot. The patch has a smooth gradient from its centre outward. Near the centre, the glow is slightly brighter. At the edges, it blends into the dim belt around the star. Above the patch, the plasma veil is thinner. It looks like a faint frost that barely catches light. The veil has a crisp inner boundary near the surface where density rises. Farther out it fades without a clear edge. The scene stays quiet and stable. It offers a payoff. When magnetospheric scattering decreases, surface emission becomes easier to interpret. Edges are less smeared. Gradients reflect temperature more directly. One number anchors the timescale safely. A strong magnetar phase can last about 10,000 years, like a coastline reshaped by many seasons before it looks settled. The comparison's about slow change, not about water. It keeps the timescale tangible. It also sets up a scale shift. A burst lasts less than a second. A flare tail can last a day. A strong phase can last thousands of years. Beyond that, the star can remain as a cooling remnant for far longer. The magnetar's story is therefore layered. Fast events sit inside slow evolution. The environment remembers the fast events as structures that persist. The star remembers them as a history of stress release and field relaxation. Another visual anchor arrives in the nebula. A bright filament near the rim now appears frayed. Its once sharp inner edge is softer. The filament breaks into parallel strands. Between strands, darker gaps widen. The overall arc remains. Yet the fine structure thins. This is the nebula's version of decay. Expansion stretches everything. Cooling reduces emission. Turbulent mixing blurs edges. The magnetar's later winds are weaker and carve less sharply defined cavities. The result is a shell that becomes more transparent and more diffuse with time. The micro-payoff is immediate. The nebula does not only grow, it also fades. Its filaments are temporary patterns in a long expansion. A second micro-payoff follows from the star's spin. Rotation slows gradually as the star loses angular momentum to its outflows. Early on, outflows are stronger and braking is more efficient. Later breaking is weaker. The period can still change, but the rate of change slows. This means the star's timing becomes more stable on short scales, even as it becomes less dramatic in emission. Stability is not excitement. It is simply a consequence of fewer disturbances in the magnetosphere. The quiet phase can therefore be easier to model in some respects, yet it becomes harder to detect because the signals are fainter. A limit of observation appears, and it is specific. Decay cannot be watched directly over a full 10,000-year span. The inference must come from populations of objects at different apparent ages. Those ages are uncertain. They can be estimated from spin and spin down, but that method assumes breaking behaves in a simple way. Magnetars do not always follow simple breaking. Timing noise and sudden changes can distort age estimates. The nebular age can be estimated from size and expansion speed, but expansion speed is not uniform and the surrounding medium is not uniform. Cooling age estimates depend on uncertain surface composition and magnetic geometry. These uncertainties limit the ability to draw a single clear timeline for any one object. The broader trend is still supported. Fields weaken, activity declines, yet the details of when and how fast remain blurred by model assumptions and measurement limits. The boundary is not a failure. It is a reminder that long-time scales must be reconstructed rather than directly observed. The section returns to the faint surface patch and the thinning veil. The halo around the star is smaller and calmer. The nebular rim is still present but less bright and less sharp. The interior cavity is larger and softer. The whole system drifts toward invisibility while continuing to expand. The next checkpoint moves outward again beyond the nebula to consider how magnetars contribute to the wider galaxy over long spans. The following section explores what remains after activity fades and how a quiet remnant still influences its neighborhood through gravity and subtle radiation. Even after the brightest years fade, a magnetar remains a heavy quiet point that shapes its surroundings in subtle ways. Gravity persists, and a low glow can still change nearby matter over long spans. At this distance, the old supernova shell is wide and faint. Its boundary is barely traced by a few surviving filaments. Those filaments look like thin smoke strands stretched into long arcs. Between arcs, the background darkness is deep and clean. Near the center, the magnetar's halo is now a soft haze with a gentle gradient. The haze has no sharp edge. It simply thins until it disappears. The first unlock is calm. The most lasting influence is not the flare but the steady presence of mass and the slow drift of radiation. The mass holds a gravitational well. That well bends paths of nearby particles and gas. The radiation is faint, but it is persistent. Over long times it can heat thin gas slightly and change its ionization state. The environment is not remade in a day. It is nudged over millennia. Ionization is atoms losing electrons and becoming charged. The definition is short and clean. The consequence is easy to hold. Charged gas responds to magnetic fields. Neutral gas responds less. Even a faint magnetar can therefore matter, because it can help keep a small region of gas in a more reactive state. A calm analogy supports the idea without forcing it. A nightlight does not brighten a whole house, yet it changes a small corner and makes shapes visible there. The magnetar's late glow is not a lamp, yet the safe point stands. A weak source can still have local effects if it shines steadily for long enough. The second unlock follows. In a thin, medium, small energy inputs matter because there is little to absorb them. A weak glow can keep a tenuous halo slightly warmer than its surroundings. That can change pressure. A small pressure difference can slowly move gas. It can blur a boundary. It can widen a cavity that was once sharp. It can also affect how dust grains charge and how they drift. The physical details remain gentle. Gradients become the story. Boundaries soften, edges fray. A slow visual anchor forms close to the magnetar. A faint crescent-shaped dimming appears in the haze as if a subtle shadow is carved into the halo. The shadow is not an object blocking light. It is a density dip where fewer particles scatter radiation. Along the inner rim of the crescent, the haze is slightly brighter. Along the outer rim, it fades. The crescent curves like a shallow bowl. It points toward a region where the interstellar medium is denser. The shape suggests motion through the medium. It suggests a bow-like compression on one side and a wake on the other. The payoff is immediate. Even a quiet remnant can reveal the direction of its environment through a symmetry. One number anchors the timescale safely. The shell can take about 100,000 years to blend into the interstellar medium like ink, slowly dispersing in a still pond until the outline is gone. The comparison is about fading, not about liquid behavior in space. It keeps the sense of gradual erasure. It also introduces a scale shift. A flare is less than a second. The shell's fading is tens of thousands of years. The magnetar's mass and faint radiation persist through both. Over that long span, the shell becomes less of a boundary and more of a subtle texture in the background gas. Another visual anchor arrives farther out at the shell edge. A surviving filament is seen as a thin arc with knots spaced along it. Each knot is a slightly denser clump. The clumps have sharper edges than the surrounding haze. Between them, the arc thins and breaks. The arc casts no hard shadow. It is too faint, yet it creates a faint contrast. On one side of the arc, the background is slightly brighter because of scattered light. On the other side, it is slightly dimmer. The arc is therefore still a boundary marker. It shows where density changes. The micro payoff is immediate. Boundaries can persist long after the driving force weakens, because expansion and mixing are slow in a thin medium. The second micro payoff follows from gravity. A signal would pass near the magnetar and experience a small deflection. The deflection is tiny. It is not a dramatic bending into a loop, yet it exists because mass curves space-time. This effect is constant. It does not depend on magnetar activity. It is part of the remnant's quiet signature. Over long times, gravity also helps retain any bound debris close by. That debris would be sparse. It might form a thin, irregular belt of particles. If present, it would not shine brightly. It would be a faint scattering structure. It could add a slight ring-like enhancement to the halo under certain viewing angles. The picture remains gentle. It is not a prominent disk. It is a subtle possibility. A limit of observation appears and remains specific. In the late phase, signals are faint. It becomes hard to separate the magnetar's emission from background sources in the galaxy. It becomes hard to measure subtle heating or ionization in nearby gas. The shell's filaments can be too dim to map fully. The density dips and crescents can be confused with unrelated interstellar structures along the same line of sight. Models that infer local heating depend on assumptions about gas density and composition. Those properties are often uncertain. Time evolution is also slow. Changes cannot be tracked easily within a human lifetime. This limits direct confirmation of the long fading process for any single object. Instead, the late phase is reconstructed by comparing many remnants at different apparent stages. That reconstruction is informative but not perfect. The boundary of certainty is calm. The remnant influence is real. The details of local structures can remain ambiguous. The section returns to the crescent dimming near the magnetar. Its inner rim remains faintly brighter. Its outer rim continues to dissolve into the background. The old shell filament arcs stretch and thin. The whole region becomes less a distinct object and more a gentle texture in the interstellar medium. The next checkpoint widens further. The following section explores how magnetars fit into the larger population of compact remnants and how their brief extreme phase influences the distribution of energy and fields in the galaxy. A magnetar is rare, yet its brief extremes can ripple into patterns that matter across a galaxy. The object belongs to a wider family of compact remnants, but its magnetic imprint is unusually sharp. At this distance, the old shell is almost gone. Only a few dim arcs remain. The background medium is a soft tapestry of faint haze and darker lanes. In one lane, the haze has a gentle gradient that narrows toward a point. That point is where the magnetar sits. Around it, the remaining halo is a small blur with a slightly brighter rim. The rim is not a ring of matter, it is a boundary and scattering efficiency. The first unlock is calm. Magnetars do not dominate by number, they dominate by intensity during a short window. That intensity injects energy and ordered magnetic structure into surrounding plasma. The energy disperses. The structure can persist as altered field topology and charged particle populations. The galaxy is threaded with magnetic fields on many scales. A magnetar can locally strengthen and disorder those fields, then leave them to relax. Field topology is the arrangement of field lines in space. The definition stays short. It matters because topology controls where particles can travel and where they become trapped. A familiar analogy keeps the idea gentle. A braided river splits and rejoins. Its channels guide flow without needing walls. The magnetar's field is not water, yet the safe point holds. Paths and connections shape motion. A change in connections changes where motion concentrates. The second unlock follows. A magnetar's outflows concede turbulence in the surrounding medium. Turbulence is chaotic motion across many scales. The definition is short and clean. In a tenuous plasma, turbulence can twist magnetic fields and mix energy through eddies. It can also accelerate some particles to high energies. Those particles then wander along the galaxy's magnetic scaffolding. Over long times, their paths spread far beyond the original remnant. The magnetar's contribution becomes diffuse like a small dye drop that eventually colours a large volume faintly. The analogy is distinct from earlier ones. It supports the idea of dilution without forcing literal behaviour. A slow visual anchor forms as a wide view of a spiral arm region. The medium appears as overlapping curtains of faint glow. Some curtains have sharper edges, some have smooth fades. Across them thin filaments of brightness run like threads in fabric. Where filaments intersect, small knots appear. The knots are denser pockets. The filaments are magnetic and density structures traced by emission. The scene is quiet and broad. It offers a micro payoff. A single compact remnant can become invisible, yet the structures it helped stir can remain visible as patterns in the larger medium. One number anchors scale safely. A typical spiral arm region can span about 1,000 light-years, like a long voyage of light that lasts a millennium. The comparison is simple. It sets a scale shift from the magnetar's tens of kilometers to a region thousands of light-years across. The shift is gentle. It does not require a leap in imagination. It is a slow zoom outward. The magnetar becomes a point. The nebula becomes a smudge. The smudge becomes one thread among many in a wide luminous fabric. Another visual anchor arrives closer in at the boundary of an interstellar cloud. The cloud edge is a soft wall with a scalloped outline. Along the outline, a faint glow brightens in patches. Those patches align with thin streaks that point back toward the magnetar's former position. The streaks are not beams, they are channels of slightly different conditions. They mark where earlier outflows or particle populations nudged the cloud boundary. Over time, the boundary smooths, yet some scallops persist as memory. The payoff is immediate. Even when the source fades, the medium can carry fainter symmetries that trace past disturbances. The third unlock follows. Magnetars may also influence the distribution of magnetic reconnection events in their vicinity. Reconnection is field lines rearranging and releasing stored energy. The definition remains short. It matters because it converts magnetic energy into heat and particle motion. A region seeded with tangled fields can undergo reconnection more readily as it relaxes. That can produce intermittent heating in surrounding plasma. It can also produce faint flashes at wavelengths that are difficult to isolate. The process is quiet at large distances, but it can be significant locally. It adds to the galaxy's background of small energy releases. The scale shift appears again in time. A reconnection event can happen quickly. The relaxation of a disturbed region can take thousands of years. Over millions of years, spiral arms move and clouds form and disperse. The magnetar's influence is therefore a brief touch that fades into a slow flow of galactic evolution. The galaxy keeps accumulating such touches from many remnants. Each one is small. Together they contribute to the texture of magnetic fields and energetic particles. A limit of observation appears and it stays specific. It is difficult to attribute a particular large-scale pattern to a particular past magnetar. Magnetic fields are hard to map in 3 dimensions. Emission that traces fields can be produced by many processes. Turbulence mixes signatures from multiple sources. A cloud boundary may have been shaped by stellar winds from other remnants or by shocks unrelated to the magnetar. Without a clear chronological marker, association is uncertain. Even when a faint streak points back toward a source, projection can mislead. The line of sight can overlay unrelated features. Models must therefore treat magnetar influence statistically. Patterns across populations can suggest a role. Single cases are harder to prove. This boundary remains calm. It does not remove the influence. It sets the level of confidence. The section returns to the wide spiral arm curtains. Filaments remain, knots remain. The faint streaks near the cloud edge fade as mixing continues. The magnetar's last clear signature becomes the quiet density of its gravitational point, while its magnetic and particle influence disperses into the wider field. The next checkpoint turns toward a gentle resolution. The following section gathers the arc into a soft landing, returning from wide galactic scales to the calm simplicity of light travelling onward through darkness. A magnetar's story ends without a sharp line because its traces thin out rather than break. The galaxy keeps the imprint as gradients, faint arcs, and quiet changes in charged gas. At this distance, the spiral arm curtains are still visible. Their filaments are softer now. The earlier knots are less distinct. The region looks like layered mist with a few darker lanes carved through it. One lane curves gently. Along its inner edge, a faint ribbon of glow follows the curve. The ribbon is smoother than the surrounding haze. It marks a boundary where charged particles drift differently. The first unlock is calm. The magnetar's legacy is mostly distributed, not concentrated. Energy injected early spreads into a larger volume. Magnetic irregularities relax and mix. Particle populations diffuse and lose energy. What remains is a subtle change in how the local medium responds to fields and radiation. The 3 core ideas are simple. Diffusion spreads things out. Relaxation smooths structure. Residual fields guide charged particles. Diffusion is the slow spreading of particles from dense to sparse. The definition stays short. The everyday image is clear. A drop of scent in air spreads until it is everywhere faintly. The air is not space, yet the safe point holds. Spreading turns a strong local signal into a weak widespread background. This helps explain why a magnetar can be dramatic nearby and almost invisible later. The second unlock follows. When particles diffuse, they do not fill space evenly at once. They follow magnetic paths. They can linger in regions where field lines loop or tangle. They can avoid regions where field lines open and allow escape. This creates faint anisotropy. It creates ribbons and lanes. It creates gradients that look like gentle brushstrokes across the arm. A slow, visual anchor forms around one such ribbon. The ribbon has a brighter inner edge and a dimmer outer edge. The inner edge is sharper because the density gradient is steeper there. The outer edge fades because diffusion smooths it. Along the ribbon, tiny ripples appear like scallops. Each scallop is a small density enhancement. Between scallops, the ribbon narrows. The ribbon also has a slight twist. Its centerline curves and then straightens. The twist suggests a field structure that is not perfectly aligned with the spiral arm flow. The payoff is immediate. The magnetar's influence can survive as geometry even after brightness fades. One number anchors the timescale safely. Over about 1 million years, the medium can mix enough that many local signatures become hard to separate, like footprints on a beach after many tides. The comparison is about gradual erasure. It keeps the timescale tangible without needing dense numerals. It also sets a scale shift. A magnetar burst is shorter than a second. A strong magnetar phase is thousands of years. The mixing that hides its traces can take 1,000,000 years. The same physical world holds all of these clocks together. The contrast is quiet. It is not meant to shock. It is meant to settle the sense of gradual smoothing across time. Another visual anchor arrives at a larger scale. A wide sheet of faint emission stretches across the field. Its brightness is almost uniform, yet a broad, oval dim region sits within it. The dim region has a smooth boundary. It looks like a shadow, but it is a low-density zone. The oval is several light-years wide. Along its edge, the sheet brightens slightly because the density increases. The oval could be a relic cavity from many sources. It could also be a region where turbulence has mixed the plasma more thoroughly. The micro-payoff is gentle. Large-scale structure can remain even when the source that helped form it is gone. The galaxy is full of overlapping relics. Some are clear, many are ambiguous. A third unlock follows from relaxation. Disturbed magnetic fields do not stay tangled forever. They relax by transferring energy into smaller-scale motions and heat. As they relax, they change how they guide charged particles. Early on, the guidance can be sharp, creating narrow ribbons. Later guidance becomes softer, creating broad gradients. This is why the ribbon's outer edge fades. The outer edge is the mark of time passing. The inner edge remains sharper because it is maintained by a persistent difference in conditions such as a density boundary in the underlying medium. The concept remains grounded. Boundaries in density can outlast boundaries in particle populations. The magnetar's influence therefore merges with the galaxy's existing structure. It becomes one ingredient rather than a standalone feature. A limit of observation appears and it stays specific. At large scales, cause and effect overlap. Many remnants contribute energy and particles. Turbulence stirs everything. Magnetic fields are hard to map in 3 dimensions. Emission can be produced by multiple mechanisms that look similar in projection. It is difficult to say whether a ribbon is shaped by a past magnetar by another compact remnant, or by a shock from a different event. Time ordering is also hard. A ribbon may persist while the source has moved. A cavity may be older than the surrounding filaments. Without a reliable clock embedded in the structure, attribution remains uncertain. Even when models match a pattern, the fit can be non-unique. This boundary does not erase the story. It places it gently in the category of probabilistic inference. The section returns to the curved lane and its faint ribbon. The scallops soften as diffusion continues. The brighter inner edge becomes less sharp. The ribbon becomes a broad gradient in a wide mist. The oval dim region in the larger sheet becomes harder to trace. It merges into the background. The galaxy continues to carry many such faint traces layered and mixed. The next checkpoint is the final one. The following section settles the arc into quiet resolution, returning to the simplest elements. A distant glow, a boundary fading, light travelling onward through darkness without strain. The strangest objects do not need drama to remain strange. A magnetar breaks rules by changing what feels like empty space. At this distance, the remnant region is quiet. The bright edges have faded. The last clear shapes are soft gradients in thin gas. A small dark point remains where the compact remnant sits. Around it, faint dust forms a broad haze with no sharp boundary. Light behaves as a traveller that carries memory without intention. It moves through dust. It moves through fields. It arrives altered in ways that are subtle and real. The first calm unlock is simple. A magnetar is not defined by size. It is defined by a magnetic field so intense that it competes with other forces nearby. That field is strongest close to the surface. Its influence weakens quickly with distance. This is why the monster feels both intimate and distant at once. Close-in physical rules shift. Far out, the galaxy continues almost unchanged. The checkpoint is a gentle inward drift. The compact remnant is seen as a dark sphere with a thin surrounding glow. The glow is not a flame. It is a faint structured region where charged particles follow constrained paths. The glow has a brighter rim on one side. The rim appears where particle density changes along a boundary. The boundary is smooth in places, it is scalloped in others. This is a physical detail that persists because gradients persist. The second calm unlock arrives. Magnetars radiate and relax. Over time, the field weakens. It does not vanish in a single moment. The weakening is slow compared to any burst. A safe number holds the scale. The strongest phase can fade over about 10,000 years, like a river taking a long time to shift a bend. The comparison is quiet and natural. It anchors time without needing fine detail. It also places the story on a wide clock. A burst lasts less than a blink. A crust can strain and release in moments. The field can unwind across thousands of years. The surrounding medium can mix across much longer spans. The scale shift is soft. It turns the story into layered time rather than a single event. A visual anchor returns close to the surface but with new texture. The sphere is nearly black. A narrow band around it is slightly brighter. The band is not an equator drawn in paint. It is a region where emission is more efficient due to field geometry. The band's edge has a gentle fall-off. The fall-off is like fog thinning at the edge of a valley. The analogy is the primary one and it remains unique. The fog does not push or pull, it simply thins. The magnetars near space behaves in a similar way. Intensity thins with distance. Structure becomes soft. The third calm unlock is about light itself. Polarization is the preferred direction of light's vibration. The definition is short and clean. In many regions, polarization is scrambled. Dust and fields can align it again. In a strong magnetized environment, empty space can slightly favor certain polarizations. This changes how light scatters in nearby dust. The effect is delicate. It is not a spotlight. It is a faint tilt in probabilities, yet it is a real clue. A signal would carry that tilt outward. It would fade as other regions mix it. The payoff is immediate. Even when the magnetar grows quiet, its neighborhood can still leave a faint signature in how light is oriented. Another visual anchor forms farther out in the surrounding haze. A wide sheet of dust looks almost uniform. Within it, a very faint fan shape appears. The fan is not bright. It is a subtle gradient in scattered light. The fan's edges are smoother than any shock front. The fan changes slowly as angle changes along the line of sight. It hints at a field-aligned structure. The physical detail is clear. A boundary exists, but it is a boundary of orientation and scattering. It is not a wall of matter. This is how the monster leaves a gentle footprint. The next checkpoint steps back again. The compact remnant becomes a point. The dust fan becomes a faint shading. The wide region becomes a soft patch among many. The galaxy's magnetic background becomes the stage. The magnetar becomes a brief variation in that stage. The fourth calm unlock arrives in the form of limits. The interior of the compact remnant remains hidden. The crust and core cannot be observed directly. Only indirect signals escape. Only radiation and timing patterns leave the surface region. Models fill the gap. These models rely on assumptions about matter under extreme pressure. They also rely on simplified geometries for magnetic fields. The uncertainty is specific. Degeneracy means different internal structures can produce similar external signals. Resolution is also limited. A distant region can blend structures along the line of sight into one shape. This makes it hard to map the true three-dimensional field. The story remains stable even with this limit. The exact microphysics can vary. The core idea holds. A compact object with an extreme magnetic field changes how particles move and how light behaves nearby. A final visual anchor settles the arc into calm. The view drifts into interarm space where gas is thinner. The background is darker. Only a few faint grains of dust scatter light. In that sparse region, a narrow ribbon of faint glow is absent. Instead, the field is quieter. The light is less shaped. The darkness is not empty. It is a medium with low density. It is a place where a signal can travel for a long time without much scattering. A small payoff lands gently. The monster breaks rules only where conditions allow it to matter. Where density is low and fields are ordinary space, behaves closer to expectation. Where density rises and fields strengthen, expectation fails. The arc therefore resolves into context. Extreme physics is local. The universe is mostly quiet. Yet it contains enough local extremes to keep its laws honest. The closing checkpoint returns to the simplest pieces. A compact remnant rotates. Its field relaxes. Dust scatters light. Gradients soften. Boundaries fade. The Magnetar becomes less of a headline and more of a quiet marker. It marks where magnetism becomes structure. It marks where light can carry orientation. It marks where matter sits at a boundary of known states. The next step is not a new mystery. It is a slower breath outward. The galaxy continues to glow faintly. The darkness between structures remains wide and calm.